All right, today we are diving into a really fascinating cosmological detective story. Scientists basically put two completely different ideas about our universe on trial, using real data from the cosmos itself, to see which one holds up.
So what's the big mystery here? It really boils down to this. Is the universe, with all its galaxies and clusters, just a tiny little ripple on the surface of some incredibly smooth and uniform beginning? Or is all that complexity, that structure, something way more fundamental? Something that's always been there and never really goes away, no matter how far out you look?
Okay, so let's get into it. Like any good mystery, we've got two main suspects, two totally competing stories for how everything came to be.
In one corner, we have Model A, what we're calling the smooth origin. The idea here is that the universe kicked off in this super uniform state. All the structure we see today, it's just a small imperfection. And if you could zoom out far enough, all those differences, those anisotropies, they would just fade away into perfect smoothness. Then, in the other corner, you've got Model B, the eternal structure. This one says, nope, there was no single smooth beginning. Instead, structure and complexity are baked into the fabric of the universe, and they exist at every single scale always.
So you've got these two huge, competing stories. How in the world do you figure out which one is right? Well, you look for clues. And that's exactly what scientists did. They set up an investigation using 5 specific statistical tests on real data from supernovae and galaxies to see which story the evidence actually points to.
All right. Our first clue comes from the Hubble constant, which, measures how fast the universe is expanding. The test asks a really simple question. If we measure this expansion rate in different directions in the sky, do we get the same number everywhere? And the answer they found is nope. The data shows a variation from one direction to another of about 5.2%. Now here's the key part. The smooth model, Model A, predicted a really tiny variation, only around 2%. But the structured model, Model B, it was expecting something higher, around 8%. So that 5.2% we actually see, it's way more in line with what Model B was expecting. So chalk one up for team structure.
Okay, on to our next piece of evidence. This test takes that last idea and pushes it even further. It's looking for the single biggest difference in the expansion rate you can find between any two opposite halves of the entire sky. It's basically trying to find the universe's most lopsided direction.
And the result they got is a whopping 3.9% asymmetry. Now, the smooth origin model expected this number to be tiny, less than 1%. A value of nearly 4% is a huge headache for that model, but it fits pretty comfortably inside what the eternal structure model was predicting. So that's another really strong piece of evidence pointing toward Model B.
All right, test number 3. This one looks for a link between the amount of stuff and how fast space is expanding. The logic seems simple, right? Places with more galaxies have more gravity, so they should expand just a little bit slower than the emptier parts of space. The question wasn't if this happens, but how strong that connection is. And here's where we get a twist. The data shows a correlation that's pretty much zero. There's no real link between how dense a region is and how fast it's expanding. Now, this was a surprise for both models, but the smooth origin model only predicted a very weak effect to begin with. The eternal structure model expected a much stronger connection. So a near zero result actually lines up better with Model A. The score is now 2-1.
So for our fourth clue, we're looking at the leftovers. See, after scientists fit their standard models to the brightness of thousands of supernovae, there are always these tiny little errors left over. They call them residuals. This test asks, are those errors just random noise scattered all over the sky, or do they actually clump together, where supernovae in one patch of sky tend to be just a little brighter or dimmer than the model expects?
What they found was a clustering score of about 0.1. So Model A predicted a score really close to 0. Pure random noise. Model B, on the other hand, predicted a higher score, around 0.2, because it expects more of these regional patterns. The actual result lands pretty much smack in the middle, so this clue is neutral. It doesn't really favor either suspect.
And that brings us to our final and maybe the most critical test. This one gets right to the heart of the whole debate. It measures something called alpha, which basically tells us what happens to the universe's lumpiness as we look at bigger and bigger scales. Does everything average out and get smoother, or does that structure stick around?
The result is a positive alpha, plus 0.141.
Now, here is why that is such a huge deal. A smooth origin universe requires a negative alpha. It has to get smoother as you zoom out, that's the whole idea. But the data shows a positive alpha, which means the structure isn't fading away, it's persisting. This is a massive, massive win for the eternal structure model.
Phew. Okay, the investigation is over. It's time to lay all the clues out on the evidence board and see exactly where things stand before we call it. So let's just run through it. Test 1, the directional variation, that went to Model B. Test 2, the big hemispherical difference, strongly favored Model B. Test 3, the density correlation, was at surprise point for Model A. Test 4, the supernova leftovers, was a wash, neutral. And finally, Test 5, that crucial scale dependence, was another huge vote for Model B. So when you tally it all up, it's 3-1 in favor of eternal structure, with one clue that was inconclusive.
But, science isn't just about counting up wins. You can use a really powerful statistical tool called a Bayes factor to weigh all 5 of these clues together, taking into account how strong each piece of evidence is. It boils everything down into one single final number.
And that number is pretty staggering. Based on this data and the specific models they tested, the odds favor the eternal structure idea over the smooth origin idea by a ratio of about 3,400 to 1. In the world of statistics, that's what you call very strong evidence. Okay, a number like 3,400 to 1 sounds dramatic for sure. But what does it actually mean for how we think about the cosmos? Let's get beyond the stats for a second.
If Model B is a better way of looking at things, it means that all this lumpiness, all these directional differences, they aren't just some leftover flaw from the Big Bang. They're a fundamental, ongoing part of what the universe is. It paints a picture of a cosmos that's less like a single smooth explosion and more like a recursive, information-based system that just keeps building structure on top of structure forever. It's a universe built with local rules, not one that started from a single global master plan.
Now, we absolutely have to put this in perspective. This is super important. This one experiment, no matter how cool it is, does not overthrow standard cosmology overnight. That 3,400 to 1 number is really dependent on the specific starting assumptions they made for each model. The best way to think of this is as a proof of concept. It was a really clever test designed to pit a very, very smooth universe against a persistently structured one. It's not the final word.
And so this all leaves us not with a neat and tidy answer, but with an even deeper, more mind-bending question. This kind of research really challenges our most basic ideas about the cosmos, because if the evidence keeps pointing away from a single, smooth, uniform starting point, then it forces us to ask, what in the world was the beginning? Or was there even one at all? Definitely something to think about.